in movies and in dramas, when they're trying to tell the audience that, oh, when the character is in a very bad state, very bad tough time in life, and the universe is trying to tell the character that there is hope, it's not all over. So how do they represent it? They usually represent it through silver lining. This is what we call silver lining. Essentially is light rays just penetrating through the thick clouds, so you have some rays of light shining through, right? So when the characters looks at this silver linings, it gives hope. Yeah. So there's a saying that every cloud has a silver lining. That means there is hope. There always hope in life, right? So these are light rays, and in this topic we're going to cover about light. How do we represent light in science? And we all know that light allows us to see things. Light can reflect off surfaces, right? So how do we represent that? And what exactly is reflection, right? So we will see that in this chapter. Let's get right into it. Hey guys, what's up? Welcome back to Classroom. It's Mr. Do, and today we are going to begin on the next topic titled Ray Model of Light. Yeah, so we all know about light. Some of us may know that light is a form of energy, and most of us should know that light allows us to see things. So in this chapter, we are going to learn a couple of things, and in this video, we're going to show an understanding that how we represent light using the ray model. Okay, so the ray model is an idea, right, that represents the path taken by light, right? So first of all, what on earth is light, right? Okay, light is a form of energy. This is something that we know. We commonly call it light energy. Yeah. Okay. So also, light travels in straight lines, right? So light doesn't bend for no reason. But later on in the chapter, you would learn that when light passes through different mediums, for example, from air into water or from air into glass, light actually bends. It's a very special phenomenon called refraction. We'll see more of that in the last part of this chapter. But for now, if you look at, this is the Marina Bay Sands, right? The light works, the light display, right? You can see that all the light rays actually travel in straight lines, right? Regardless of where it's pointing at, So, sorry, that's a poor drawing, right? But you get the idea. It travels in a straight line, and this is why for interior design there is applications for laser. So for instance, you can use laser to mark out straight lines in the room for you to draw, or determine whether everything is at the same height. There is an application for that. You can check it out. Alright, so first of all, how do we represent light? A ray of light rather, in science. Okay, so how would you represent a light that comes up from this torch or this laser pointer over here? Okay, so there may be different ways. Okay, you may try imagining on your own, but for science we use a straight line, okay, coming from a light source to represent the light rays, with an arrow to represent the direction of travel of light ray. So you can see over here, right, if the grey color box rectangle here represents the laser pointer or the torch, then this green color straight line represents the laser, so-called, or the light ray, right, that comes out from this laser pointer, right? So there are two things to note here. First of all, you have a straight line. Okay, you might want to annotate down in your notes. This thing must be a straight line, so please use your ruler to draw in exams, right? Secondly, you have the arrow. Okay, the arrow is typically drawn in the middle of the line, or you may want to draw it at the end of the line, is also fine, but typically drawn at the middle. Alright, so yeah, what it means, it represents the direction of travel, the light ray. So clearly this light ray comes from the torch and moves towards the right hand side of the screen. So the arrow tells us. The arrow is very important, especially when you move on to upper sec for physics. When we deal with light, many students tend to forget to draw this arrow, right? It gives us very important information, so please do not forget. Alright, moving on. Usually when we talk about light coming from an object or light source, such as the light, the ceiling lights at home, right, or the sun, we usually say that it comes in a bundle. First of all, to begin with, light rays are not real things, right? It's just an idea, a drawing for us to represent light. Okay, so so there is no such thing as a single light ray in real life. There's no such thing, right? So when we represent light sources, light coming from different sources, we usually draw them in a bundle, right? And you usually draw them in bundles of threes, just as a representation. Remember, these arrows, they're not real things, yeah? Okay, so there are three types of bundles of light. First of all, you have the parallel rays, right? So if you recall from mathematics, what parallel means that the lines don't meet, right? They will not ever meet, pardon. Okay, never meet. No matter how far you extend them, this is parallel light rays. There's also divergent. Divergent means separate. Okay, so the light rays will separate like this, getting further and further away from each other, so called, right? The distance between the light rays will be further and further as you go. The opposite of divergence is convergent. So these light rays will meet. Okay, converge means meet at a single point over here. In this case, this is a magnifying glass. Okay, this is a magnifying glass, and it's able to focus light rays entering, passing through the magnifying glass on a single point. So some of you may know that you can actually focus sunlight using a magnifying glass to burn paper, to set paper or dry leaves on fire. Alright, we will see a video on it now.
Let us focus sun rays on a dried leaf using a convex lens and see what happens. Hold the leaf such that the sunlight directly falls on it. Now hold the magnifying lens above the leaf. You will see that there is a bright spot on the leaf, which is the beam of the sunlight focused by the lens. Observe what happens to the leaf. The leaf starts burning. Why did the leaf catch fire? The lens converged the sun rays onto a small area of the leaf. The heat energy carried by the rays are now focused on this area of the leaf. As this area receives more intense heat, its temperature gradually rises. When the temperature of the leaf reaches its ignition point, the leaf catches fire.
Alright, so you can, as you can see in the video, right? The demonstrator uses magnifying glass to focus sunlight onto the dried leaf, and because this focus point here, all the light rays are focused over there. There is high amount of energy, right? Pardon me again. Okay, so there is high energy, a lot of light energy being focused at this very point here. This is why it's able to set the dry leaves on fire, right? So that's convergent ray for you. Okay, so we all know that light allows us to see objects. Yeah, without lights we can't see anything, right? So how do we actually represent that? Using the ray model. Okay, so we are able to see light because light coming from the object enters our eyes, right? So we must draw some light rays. Okay, so here's one example, one light ray coming from the apple. There's one from the center and there's one from the base of the apple entering our eyes. Right, so light rays coming in, and then also, of course, not forgetting the leaf, right? Okay. So the point here is, at every point of the object, you can see every point of the apple, starting from the top of the leaf to the base of the apple, to somewhere in the middle, everywhere, because there is light ray coming in from the object into our eyes. Alright, so it's not just one light ray coming from the whole of the apple. In fact, every point of the object, there is a light ray entering our eyes. Okay, so that's something for you to note here. Okay, so moving on. Alright, so first of all, before we go into the next part, we all know that we can see the apple because light from the apple enters our eyes, but you do know that some objects are not giving off light on its own. Okay, so an apple clearly does not give off light of it on its own. If you enter a dark room with an apple, you will not be able to see it because it does not give off its own light. Certain things give out their own lights, like a star, our sun, or light bulb, for instance, right, or your television screen. They give out light on their own. But for all other objects that don't give out light on their own, we can see them because light from certain sources, like the ceiling lights at home, right, reflect off these objects, and these reflected lights enter our eyes. This is why we are able to see them. So probably this green light here came from somewhere, okay, so they are reflected like this, okay, so into, you know, the light from the light source hits the leaf, and then it reflects off the leaf into our eyes. This is why we can see them. Alright, sorry for the very messy diagram. Okay, let's move on. So this is why reflection comes in, right? So in this part of the video, you will learn about reflection, explain how reflection is affected by smooth and round surfaces. We will see what happens when light reflects off smooth surfaces and rough surfaces using ray model. Okay, we will draw and label a ray diagram reflected from the plane mirror. Okay, we will leave that for the next video. Okay, but definitely we'll do this. We will state the characteristics of image formed in a plane mirror, right? Mirror is something that we use every day to check ourselves, you know, whether we are properly groomed. Okay, we will define this idea called virtual as something that cannot be captured on the screen. We'll see more of that later. Okay, and the last one we'll leave it for the next video. So these two we'll leave it for the next video. Okay, so moving on from here, as we were saying just now, how do we see objects? Because lights from light sources, so-called, bounce off objects and enter our eyes, right? So in this picture here, we are able to see the flower because there is a light source, which is the sun. Okay, so source, S-O-U-R, source, light source, which is in this case the sun, right, provides the light energy, the light rays that bounces off the flower and enters our eyes, which is maybe here, right? So our eyes are here, right? Okay, this bouncing of light is what we call reflection. Like the bouncing off a particular surface. In this case, the surface is the flower. It can be walls, it can be mirror, it can be any objects like the apple just now. Okay, so that's called reflection. Right, one typical example of reflection is different phases of the moon. So we know that the moon does not give off its own light, okay? But we can see the moon, we can see the moon because of sunlight coming in from the sun over here, right? So the sunlight, you know, reflects off the moon, and then, oh sorry, the moon is here, right? It reflects off the moon and then enters our eyes. So this is why we can even see the moon to begin with. But depending on the position of the moon, okay, relative to the earth at different times of the month, we will see different shapes of the moon because of the angle that we are looking at it, right? The reflection, right? So yeah, we can see the moon because it reflects light of the sun. Okay, the phase of the moon, that's what we call, right? The different shapes from the new moon, the crescent, to the full moon. It really depends on where is the moon. So I will link a simulation to in the description below for you to see, to play around to see how different positions of the moon cause the different so-called shapes, right? From new moon to half moon to full moon, so-called, right? Okay, so you can have a view of it. Alright, so any reflection is governed by this law of reflection. Okay, so any reflection, yeah, of any surface. Okay, so reflection occurs because light rays bounce off a surface. This is what we said just now. Okay, now let's look at the diagram here. We have, first of all, there are a few terms to learn here: incident ray, reflected ray, there's a normal, angle of incidence, and angle of reflection. Let's go through them one by one. Now, if you can see the arrow head here, this tells us the direction of how the light travels, yeah? So the incident ray is the ray that enters, that comes onto the surface. Okay? So the incident ray is the light ray that approaches, so-called. Okay, you may want to write this down in your notes. Okay, it's the light ray that approaches the surface to be reflected, okay, that reflects this light ray. And of course you have the reflected ray, right? So needless to say, this is the light ray that's reflected off the surface. Okay, now there's another line here called normal. Okay, so what is normal? Normal is a line, an imaginary line. Let's look at it. The normal is an imaginary line that is perpendicular to the surface. Let's recall, what does perpendicular means? It means at an angle of 90 degrees. So where is the 90 degrees? Over here. Okay, you might want to draw this down. So this normal is a arbitrary, as an imaginary line that we imagine that is perpendicular to this surface, right? So if you're looking at your tabletop, right, your table they're working on, right, the normal to your tabletop is pointing vertically upwards. It's perpendicular to the surface. This is what we mean by that. Okay, now why do we need this normal? Because we need to label the angle of incidence and the angle of reflection. Okay, this angle of incidence here, or shorthand I, is the angle from the incident ray to the normal. From the incident ray to the normal. Alright, so let's not get confused here. Let's write it down. The angle of incidence is the angle from the incident ray to the normal. Okay, and of course the angle of reflection on the other hand is the angle from the normal to the reflected ray, yeah? Alright, so for angle of reflection we use a shorthand, small letter r, with a degree sign for angle, okay, to represent, right? So you have the incident ray, reflected ray, and the normal, and the angle between the incident ray and the normal being the angle of incidence, and the angle between the normal and the reflected ray being the angle of reflection, right? So there are a couple of names here to remember, just take note. Okay, so moving on. Yeah, so here angle of incidence, angle I, is measured from the incident ray to the normal, where angle of reflection R is from the reflected ray to the normal, or from the normal to the reflected ray, doesn't matter. Okay, so what does the law of reflection tell us? The law of reflection tells us that for any surface, right, any surface will do, a single light ray will reflect such that the angle of incidence equal to the angle of reflection. Get the idea? So for example, if the light ray enters, approaches the surface, right, at an angle of, for example, 50 degrees, right, to the normal, the angle of incidence is then 50. So by the law of reflection, we don't even need to do any calculation. We know that the angle of reflection is 50 degrees. Okay, because they must be equal. Die. No matter what surface you're talking about. Okay, so this here, these two texts here tell us is the law of reflection. Okay, moving on. So let's look at these few images here. You can see that, you know, this over here is a lake. Okay, here is a glass building. It is a building with glass external surface. Okay, glass building, and here is a mirror, kitty cat mirror, right? And this is a marble floor, right? This one you can see, right? So you can see that, you know, there is very sharp images being formed on all these surfaces. Actually, it's very clear, right? Quite high resolution in using today's terms, right? So what is in common about all these surfaces that allows the very clear image, clearly reflected image to be shown? Well, the answer is these images are sharp. First of all, these images are sharp, and it's because all these surfaces are smooth. Okay, so smooth, like if you can touch the mirror, it's pretty smooth, right? Any surface that gives us very clear reflection image, these are very smooth objects. But of course, you may argue that my tabletop feels rather smooth. Okay, but if you zoom in using a microscope, you really zoom in down to the surface, you will see that it's not as smooth as a plane mirror. Okay, so let's take a look here. What does it mean by smooth surface, and how does it give really sharp image, right? So here you can see that this surface here is really flat, really smooth, and it's like a microscopic view, right? You zoom in, magnify at the surface, you can see that it's nice, it's smooth. Okay, so why is it that it allows us to see very clear and sharp images? Is because light rays coming in parallel remain parallel after reflection. Okay, so because the surface is smooth, let's take a look. Let's look at incident ray 1, incident ray 2, and incident ray 3, right? So let's look at 1 first. Okay, 1 comes in, okay, approaches the smooth surface and reflects off according to the law of reflection. So let me draw a normal here. Oh, by the way, normal should be represented using dotted lines, right? So just take note here. Okay, so let me call it normal for arrow 1, for light ray 1, right? So for light ray 1, the angle of incidence equals to angle of reflection, I equals to R. And you can say the same thing for all the other light rays. For light ray 2 as well, okay, I can draw a normal for light ray 2. Okay, let's call this normal for 2. Okay, you can see that all the 3 light rays all obey the law of reflection, as I said just now, regardless of the surface, right? So because this surface here is smooth, is flat, all these light rays that come in parallel, they will reflect off parallel, right? So when we receive, the reflected ray from our eyes over here, let me just draw an eye here. Okay, when we take in a bundle of parallel light rays, you will see a very sharp image. Okay, that's the idea, right? So if you are able to see a very clear image, it's because the light rays entering are all parallel. But if the light rays coming in are pointed at different angles, which we will see later, then you'll get a very blurred image, not sharp image. But of course, I'm not talking about your eyesight here, right? I'm taking for granted that you have good eyesight or you're wearing spectacles. Okay, moving on. How about rough surfaces? Right, take a look. When the water surface is wavy, let's say there's a wind passing through and it's, the water surface is not calm, you can see that the reflection of the mountain here is not clear, it's not high definition, right? How about the light from the car itself? Also not clear. Same for the reflected light of buildings and street lamps, also not sharp, right? So reflections of rough surfaces are blurred or simply not sharp. Okay, that's what it means by blur. Of course, we all know what it means by blur. Okay, so why is it that reflection of rough surfaces are not sharp? Let's take a look here. Okay, same as the case just now, there are 3 light rays coming in parallel from some object. Okay, again we can call them light ray 1, 2, and 3. Now because of the unsmooth surface, you can see that all the light rays reflect off at different angles. So this is reflected ray 1. Okay, reflected ray 1. Light ray 2 reflects off here, while light ray 3 reflects off here. So you can see, after reflecting off this rough surface, light rays 1, 2, and 3 now move in different direction. Okay, they're going to travel in different directions. Okay, and we call that scattered. Okay, as opposed to the smooth parallel reflection of a smooth surface. Okay, so this kind of reflection is what we call scattered. So rough surfaces scatter incoming light rays in different directions, and because of that, the reflected rays, they are no longer parallel. You don't have a bundle of parallel light rays, they are blurred or simply no image form. If you look at the tabletop, right? Okay, chances are your tabletop is not it's not a smooth surface. You don't see very clear images of objects in your surrounding. Okay, this is because the surface is rough, and you may even see no images at all, right? So it depends on how smooth, or rather how rough the surface is and how much it scatters the incoming light rays. You may not even get any image. Okay, the more they're scattered, the more blurred the images are. They'll come to a point whereby you just don't see any more images. Then the surface is no longer reflective. Okay, so moving on. So a typical, best reflective smooth surface is a plane mirror. We all have experience using a plane mirror. Okay, you might want to pause the video and go to a mirror or pick up a handheld mirror in front of you to see for yourself. Okay, so here we are talking about the characteristics of images formed in a plane mirror. Plane means flat, yeah? Plane mirror. Okay, so let's look at number one. Image distance equals to object distance. Now what does this mean? If you're looking into the mirror, you are at a distance away from the mirror. Let's say you hold your mirror 1 meter in front of you. Alright, so for instance, this lady is at a distance of 1 meter away from the mirror. Alright, now the image, her image, will be exactly at 1 meter, so-called behind the mirror. Okay, so this is what it means by image distance equals to object distance. This distance here is the object distance. Okay, because she is the real object, yeah? And here, this 1 meter here is the image distance. Alright, okay. So, next thing is, images formed in a plane mirror is laterally inverted, left-right inverted. What do we mean by that? Okay, we will see more of that later. Upright. Okay, this upright is virtual and it's same size. Okay, what do all these things mean? Let's look at it one by one. So just now I was saying, okay, if this is you standing in front of a mirror, this distance here, let's call it distance D, should be the same distance as the image formed. Okay, so if you were to move closer to the mirror, okay, you can try it later, or now if you already have a mirror in front of you, move closer to the mirror, you will see that your image also moves closer to you. This is because you two must be at the same distance from the surface of the mirror itself. Okay, moving on. Laterally inverted. Right, you should have this experience. You raise your right hand in front of the mirror and you see that your image is actually lifting his or her left hand. Okay, so images are left-right flipped, so-called. This is what we mean by inverted. Left-right inverted. Yeah, it's flipped, left and right. Next, upright. Upright means, well, if you're standing straight, with your head pointing up, then the head should be pointing up. I mean, the image head should be pointing up, as opposed to this. This is inverted. Okay, you might think, of course, mirrors don't produce this kind of image. Yeah, but lenses do. Okay, optical lens do produce inverted images. Alright, so just for reference. Okay, so this idea called virtual. So another characteristic of images formed in mirrors is called virtual. Virtual means not real. If you just look at the word virtual itself, in English it means it's not real. What do we mean by not real? It means that the image cannot be captured on the screen. Now this word screen can mean any surfaces, like a piece of paper. Okay, so let's look at an example here. The projectors in classrooms or offices, meeting rooms, can be captured on the screen, on the surface, right? Typically the screen at the front of the classroom. So these images are real. Okay, but on the other hand, as opposed to mirror images cannot be captured on the screen. What do I mean by that? You try to put a piece of paper between you and the mirror or somewhere near the mirror. Okay, you won't be able to see any image on the paper of yourself. The image in the mirror cannot be projected onto any screen or a piece of paper for that matter. Okay, so this images are what we call virtual. Okay, so in the next lesson we will talk about how to draw light rays to represent reflection of a plane mirror. Okay, but let's go through what we have learned in this lesson. Okay, so in this lesson we learned how to represent light rays using a straight line and an arrow. Remember, it must be a straight line because light travels in a straight line and the arrow represents the direction of travel. Okay, we also learned about reflection. Basically, the idea of reflection is light rays bouncing off certain objects or certain surfaces. Okay, this allows us to see everyday objects because light rays from certain light source bounce off these objects into our eyes. Okay, this is the idea of reflection. We also learned about the law of reflection, basically saying that, okay, when the light ray approaches a surface to be reflected, the angle of incidence, which is the angle between the incident ray and the normal, it should be equals to the angle of reflection, which is the angle between the normal and the reflected ray. Okay. We also learned that, okay, when we reflect light off smooth surfaces, okay, the light rays remain parallel and hence it creates a sharp image. On the other hand, for rough surfaces, okay, rough surfaces tend to scatter incoming light rays. That means parallel light rays coming in, after being reflected, they bounce off in very different directions. So this is why you have blur or no images. We also learned about the characteristics of plane images. Images formed in plane mirrors. Okay, so they are equal. The image distance equals to the object distance. It's laterally inverted. It's upright. It's virtual and same size of the object. Oh, this is something that I forgot to cover just now. The height, right? The size of the lady should be equal to the height of the lady in the image. In the mirror itself. Okay, so in particular, we need to be clear about what it means by virtual. Virtual means that this image can be, or rather cannot be captured on a screen. So you try to put a piece of paper, near the mirror to try to capture your mirror image. It won't happen. It just won't happen. Okay, so that's it for this lesson. I hope you learned something. Remember to fill in your notes. Okay, and I'll see you in the next topic. Take care.